Let's deep dive into the most intense section of the iron making process, the Bosch. In the world of metallurgy, the Bosch is the ultimate intersection of gas flow, chemical reduction, and fluid mechanics. As you can see from the diagram, we are dealing with a Tuyere Raceway where the gas velocity exceeds 200 meters per second and heat flux uh, to a very high extent. Now, this is a zone of extreme energy where the temperature soar about uh, more than 2000 degrees centigrades, creating the kinetics energy required to drive the entire furnace. Now, to understand the Bosch, you have to visualize it as a counter current collision zone. On one side, we have molten iron and slag descending at roughly 1450 degrees centigrade. Fighting against them is a massive volume of ascending gases, and it has a lot of thermal energy at 2000 degrees centigrade. Now, this creates what we call the fundamental conflict. Over 60% of the total pressure drop in the lower furnace happens right here because that rising gas must physically force its way through a narrow grid of solid coke that is already being choked by descending viscous liquid. But where does this gas comes from? It begins at the Tuyere Raceway. Within the first zero point 0.4 meter, oxygen is rapidly depleted, leading to an exothermic peak between zero point 0.4 and zero point 0.8 meters, where carbon and oxygen react to create localized flame temperature of 1800 to 2000 degrees centigrade. Now, we can say that the magic happens in the endothermic conversion zone, and here's the Woodward reaction occur, that is CO2 react with coke to form carbon monoxide. While this reaction consumes heat, and it is a good amount of heat, it arms the gas, leaving us with a superheated reducing agent composed of roughly 35% CO and 65% nitrogen. Now, this CO rich gas is a chemical powerhouse. As it reaches it, encounters a stride descending towards the hearth, and because of the gas arriving from the tuyere has zero oxygen and a massive oxygen potential imbalance, it aggressively forces the reduction of oosteite into pure metallic iron. This thermodynamic imbalance is critical. It ensures the iron is reduced before it fully melts and disappears into hearth below. Chemistry in the Bosch is not just about iron, it's also about silicon. Silicon transfer doesn't happen through the simple liquid contact. It's a three-step vapor phase dance. First, radiant heat above 1500 degrees centigrade volatiles silica in the slag into SiO gas. Second, this gas joins the massive upward flow of carbon monoxide and nitrogen. And finally, as the gas passes descending carbon saturated liquid iron droplet, the silicon is absorbed into the metal. Now, this fast moving gaseous phase is the primary way silicon enters your final product. Now, beyond chemistry, The Bosch serves a vital mechanical role as an aerodynamic suspension system. We have thousands of tons of body mass pushing down due to gravity. The upward thrust of high velocity gas and the resulting frictional resistance, noted here as a delta P, actually support that weight. This buoyancy is structurally required. Without this carefully regulated gas pressure, the body would collapse uncontrollably into the hearth. And once this happens, that is a big, huge mess for blast furnace. Now we enter the wet zone where the aerodynamics becomes a coke grid percolation. We monitor irrigation density, essentially how much liquid is trickling through the coke. A major challenge here is slag viscosity. Near the cohesive zone, primary slag are highly viscous and can form foams or emulsion. This glue chokes the gas pathway, forcing the gas flow to become severely compressed as it fights to move upward. And now, this brings us to the flooding cliff. Looking at this graph of pressure drop versus gas velocity, you see the two paths. The blue line is a dry bed which is stable, but the orange line, the irrigated bed, is our reality. As gas velocity increases, we hit the loading point where gas friction becomes and begins to hold liquid back and voids fill up. If we push further, we hit the flooding limit, a point of catastrophic resistance, where liquid are actually blown upward by the gas. And once this happens, our furnace goes through a erratic state uh, of air. To manage this, we use the aerodynamic state matrix. In stable irrigation, liquid descent is smooth and pressure is linear. In loading phase, we see liquid hold up and localized cooling, which is high risk, but flooding is a total failure state. Gas velocity exceeds the limit, liquids bubble and froth, and the furnace permeability is effectively choked to zero. So, when the flooding occurs, the result is furnace hanging. As liquid slag is pushed upward into colder zone, it suddenly freezes, creating an impermeable arc that breaches the furnace wall. This arch traps the high pressure gas below, leading to an extreme pressure spike. The furnace essentially refuses the blast, halting production and risking serious damage to the refractory and hearth together. So, the ultimate goal is finding the Bosch operating window. We want to maximize the gas velocity for productivity and fast reduction, but we must stay below the flooding threshold, and that is the key for each and every blast furnace operation person. The key insight here is that optimization is not just about the gas flow, it's about engineering the physical properties of the burden also. Uses a stronger coke and low viscosity slag to push that flooding limit higher, safely unlocking more productivity.